Okay. Good morning, folks. Um, can you hear me clear?
Yep, we can hear you.
Nice. Great. So let's get started from where we left again. Appreciate Anthony, Lucas, Haufan for turning on your videos. If others could turn on. I know Anthony has to leave a little bit early today. If others can turn on, so at any point I have at least a few visible profiles, few visible faces, that helps. Okay, today's goal is to really finish up talking about unlock, which is unsupervised localization, and then move on to a new topic, which is around sensor fusion for motion tracking, of course, but for how we really curb or check the divergence of IMU motion tracking, because we are realizing that there is no way that we can prevent or we can do IMU motion tracking without any help. Meaning, if as a blind person, if you're walking and I ask you to walk a straight line, there's no way you can walk. You have to touch these pianos and these computers in your environment to be able to course correct. And I hope you see how unlock is actually course correcting by using these landmarks. But the interesting thing over here is that we do not know where the landmarks are, right? So unlock is something that companies are interested in because Google, Facebook, Samsung, all these companies have data from the crowd because they have lots of people walking around in shopping malls and hotels and airports, etc. And they have this data, and from that data, if you can actually do these clustering, the data is unlabeled, meaning the people who are walking around in the shopping mall, they're not saying, you know, I am in front of Starbucks right now, I'm in front of Pizza Hut right now. They're not saying that, right? Their phones are just collecting data, IMU data, Wi-Fi data, 3G, 4G data, every sensor is collecting data, and the data is coming back to the servers. In fact, some people told me that if you look carefully into the fine prints, when you accept all the policies and stuff, one of the things that many of these companies do is that they ask you permission for 5 minutes of data every day, right? And in all those fine prints, it says that 5 minutes of data. So once you have once they have 5 minutes of data from lots of people, they have this crowdsourced data from, let's say, a shopping mall in Shanghai. And now they cannot use it as labeled data because it's not labeled. But if you can run these unsupervised clustering algorithms on these sensor patterns, then do dead reckoning, get a location of the sensors in physical space, and from that create landmarks, you have this opportunity to actually reset or course correct your IMU estimation trajectory, IMU estimated trajectory. I said a lot over there. Let me pause to see if there are questions or if the core intuition behind unsupervised localization is clear. Questions, guys?
Could I ask a question?
Go ahead.
Okay, thanks. So I was really, I missed the last lecture, but I watched the recording and I was really impressed with sort of like the whole idea of sort of, you know, you can't see these landmarks with your eyes, but you're sort of clustering them in this feature space and then projecting them back on. So I found that all really impressive, but I had one question. So I think that the accelerometer inside the phone, it sounds like it's not just directly measuring the acceleration of the phone, right? It's sort of in a different reference frame than the phone. Like if you have gravity pulling down and then normal force up from your hand, technically the phone is at zero acceleration, but if my understanding is correct, the accelerometer still feels the force of gravity pulling down at 9.8, right?
That's right.
Okay, so it's sort of in a different reference frame than
exactly. So
okay.
What you're saying is right. let's use this slide. Wait, let's use the corner of this slide quickly. Typically, we say that we think of accelerometer to displacement computation as double integration of accelerometer, right? But in this case, we could do that. We could potentially do that. But then in that case, if you want to understand how a human is moving, right? How a human is moving from his phone's acceleration, one way is we really have to first orient the phone in the global coordinate frame and then figure out what is the acceleration corresponding to this component in the forward component. If we get that acceleration, then if we double integrate that acceleration, we would be able to understand the phone's forward motion. That's one way of doing it, right? The other way of doing it is forget double integrating acceleration. That's not going to work. Someone can say this, that, hey, look, double integration of acceleration, it's too hard. I'm not going to try that. But the other thing I'm going to try is this, the phone's accelerometer data when I walk, it gives me these bouncy patterns. And I'm going to count the number of steps from it. And from some other ways, I'm going to count the length of each step. And I'm going to count, and I'm going to figure out the walking direction. And I'm going to combine all of those: step count, walk direction, step count n, walk direction theta, and step length L. So L and theta, every step L and theta is like a vector. You're going towards theta for distance L. Next step, another vector. Next step, another vector. Next step, another vector. So I add all of these steps, basically n steps, and that's also a way of figuring out how much I have moved, right? So in Unlock, they do not take the first approach. They take the second approach, or rather this approach, and then say, okay, I have some movement now, but still I won't be able to make sure that I don't diverge, right? I'll still diverge because all of these measurements are coming from IMU. And because that noise is there, I'll never be able to know my global position. So I need some landmarks to constantly correct myself or periodically correct myself. Lucas, does that answer your question?
Yeah, I think it does. So like, obviously, even though, you know, it's not centered around like zero acceleration, but it's centered around like 9.8, it's obviously not a problem.
Not a problem because
you can see the steps. So it's
exactly, that's exactly
really
right.
Matter. It's just
exactly right, because your steps are going to be around 9.8.
Okay, that actually helps with the MP1 too, because I was
exactly.
Like, why we were seeing that in MP1. So that helps. Like that kind of does make it ties everything.
Gravity is always pulling you down, so it's always there. So any measurement that you do or with the accelerometer is going to have that DC. It's going to increase the mean to 9.8, and all the other signals will be around that. Hey guys, if you do a FFT of this signal, of your IMU signal, you'll see that at 0 frequency, there is a 9.8 frequency amplitude. If you do an FFT, right, what would you see? If your walking frequency is, let's say, 10 hertz, actually not 10 hertz, right? 10 hertz is like 10 steps per second. That may be too much. Let's say walking frequency is 4 hertz, right? You're taking 4 steps per second, maybe you're jogging, right? So in your FFT, you would see a frequency at 4 hertz, right? Maybe, and because of these other motions in your body, every time you put your foot on the ground, there are vibrations happening on the body. There will be other frequency components that will go all the way to high. But you'll also see at 0 a strong component of 9.8. Right? What is this 0? This 0 is this horizontal straight line. That's called the DC. That's frequency 0. It's a straight line. There is no frequency. It's no sinusoid. It's basically a sinusoid with 0 frequency. And that's often called the DC offset. If you make your accelerometer reading mean 0, Right? If you subtract the mean from it, this DC component will go away. Right? Yeah, perfect.
Cool. Thanks for going over that.
Right. Okay. Okay, I'm just looking at the chat. Okay, there's too many. Sorry. If there's something you want to chat about, not on the chat, but in live, please speak up. Great. So we said that the key intuition out here is that, oh, I did all these markings, but that's okay, is that multiple people are going to walk. They're all going to encounter the same sensor signature, but their estimate, their PDR of that sensor signature, their location estimate of that sensor signature is going to be different. The errors across different people would be uncorrelated. And as a result, we can think of this as a distribution, each of the landmark location estimates, and we'll take the mean of that distribution through a maximum likelihood estimate. And once we get the mean, we say, my estimate of the landmark is wrong. Actually, the landmark is here. Therefore, I correct my PDR based on that landmark location, and I keep doing that. Guys, is that intuition? If you get this intuition, you've gotten the whole thing. Is that intuition clear? Imagine there's a water fountain over here. This is a water fountain, let's say. John walks. This is John. John walks, is doing PDR, dead reckoning. And then he estimates because his PDR is wrong, he estimates the location of the water fountain to be here. This is John's estimate. Susan walks. Her PDR is pretty bad as well. She estimates it over here. This is Susan's estimate. Another person walks. Let's say that person is Mary. Mary estimates it over here. Right? So now if you have many such estimates, and let's assume that the error is Gaussian, you can say, oh, if these three are the points, estimated points, or let's say there are many more, then you can say the actual maximum likelihood estimate of the water fountain is over here. Right? So then Mary, John, Susan, everyone can say, oh, you know what? So Mary says, my estimate should actually be moved to here. So when I was walking this rest of this path, I should move that path from here. Because I was actually not at this location, I was actually at this location, because that's the landmark location. Right? So Mary moves her path, John moves her path, everyone moves her path to the estimated landmark location. And now the next landmark that you encounter, let's say that's a computer server room, which has a magnetic landmark, let's say, you again estimate the landmark based on the corrected path. Okay? And this is the way you estimate all the landmarks. And remember, the better landmarks correct your PDR. The better PDR corrects the landmarks, and this keeps happening. So remember, the landmarks are growing gradually. Everyone is, let's say, everyone is starting from the entrance of the shopping mall. So the first person walks, the second person walks, the third person walks. So this is why the first landmark that gets estimated is this landmark, which is closer to everyone's starting point. And once this landmark is estimated, then this landmark is estimated, because most of the data goes through this landmark. So all I'm trying to say is there is an ordering in which the landmarks should get estimated. And that ordering is based on the landmark that has seen the least dead reckoning error should get estimated first. Right? If these people have walked around and then in the shopping mall they've come over here, many of those people have walked different paths and have come over here. And now if you estimate this landmark first, there's a problem. Why? Suppose this is the first landmark you estimate, where people have started over here and they've walked a very long path. John's answer is there's more variance. There's huge variance, right? So if you think of the estimated landmark, the estimated points, John would estimate this landmark as somewhere here. Mary would estimate this landmark here. Susan would estimate this landmark here. So from the sensor space, when you project it back into the physical space, you won't even see a cluster in physical space because they are so scattered around. Right? So yeah, John says garbage in, garbage out. It's more like long PDR in, garbage out. Because if you've done PDR for 10 minutes and then you try to see clusters, you're not going to see anything. Because by that time PDR has diverged. So until PDR has not diverged too much, within that time you need to do your correction. Otherwise you're in a bad situation. Right? So this is the reason nearby landmarks from the starting point gets estimated first. Using that as an anchor, the next landmark gets estimated next. Using that next one as an anchor, the next landmark gets estimated. Okay, so the ordering in which the landmarks get estimated is important. Very good. And then once you have these different points or estimated points, you can treat them as a distribution. You compute the maximum likelihood position of the landmark location. You also treat the humans location. This is your PDR error. You assume there are different users have independent errors, and then you put the whole thing together. This is what we talked last time. The unlocks error keeps growing. Then you see a landmark, you go down, you reset your error. Again, it keeps growing. You see another landmark, you reset. Of course, the resetting error may not go down to 0 because your estimated landmark in the system may not be precise. You may not precisely know where the water fountain is, right? But that's okay, right? As long as your PDR error gets reduced, you're fine. So the error keeps growing, comes down, keeps growing, comes down. And that is what you'll see in the paper. You're supposed to read the unlock paper and review it. Okay, so here is the basic algorithm, the recursive or the iterative unlock algorithm. Imagine you already have the landmarks. Imagine that. Okay, so you already have these landmarks and the locations of these landmarks. If you pretend that is true, then it's not difficult, right? Because you take the user's motion traces, which is the IMU data, you do dead reckoning, and you use the landmarks to correct PDR, right? You will get user's location error. I hope this part is clear, right? This is simple. Right? I have landmarks, I have PDR, I'm doing PDR, periodically I'm correcting it. So this part is exactly this part. I'm periodically correcting my PDR with landmark locations. But what unlock is saying is, look, I can also take my user's motion traces, the IMU data, and I create unique sensor fingerprint. From that, I find landmark locations, but I find landmark locations using the dead reckoning. right? If the user is moving, then I roughly know the user's location. And if I see a landmark, I can estimate the landmark's location from that PDR itself. And once I estimate the landmark location, I update my list. I have a bunch of landmarks. They're all bad locations. So I improve that landmark locations list. And now what do? I feed this back over here. So landmark location error goes down. And once I feed back, actually, how do I delete this? Let me see. Draw, delete. Yeah. Good. Yeah. So once I feed back my updated landmark list into here, I have better landmarks now, so my PDR will be better. If my PDR is better, when I use my PDR for landmark estimation, the landmark estimation will be better. So as I get more and more data from people, my landmark error drops, my user location error drops, and that keeps happening until it has stabilized. After some point, you cannot reduce it anymore. Make sense? Great. So here is one graph which shows the localization error in meters. And this is CDF, this is cumulative distribution function. So it roughly says that unlocks median error. And this is basically how much of data did you get? Meaning, when someone walks in this whole building for half an hour, just walk around for half an hour in a building that is of the size of, let's say, ECEB ground floor. Okay. So if you walk around half an hour in that ground floor, you don't have to do anything. You just take your phone and you walk around randomly. Right? From that half an hour of data, this is what the result looks like. So median error is around 5 meters. If you walk 1.5 to 2 hours, your data becomes, your improvement is quite a bit. It's around 2 meters. Okay. So in some sense, and it's not that one person has to walk. What this means is how many man hours. So 2 man hours means 2 people can walk 1 hour each. 1 person can walk 2 hours. 4 people can walk half an hour each. It doesn't matter, right? I basically want 2 man hours of data or 2 person hours of data. So this is what the localization error roughly looks like. But the error is not the more important part. I think the more important part is I did not ask for training data. Right? That's the key. Right? I did not ask for training data. So median is 1.63 meters. Okay. So to finish up, Charles Lindbergh used stars as a way to navigate himself from New York to Paris. Unlock is saying we don't have stars in indoor environments to solve the indoor localization problem. But given that we are living in a matrix, if you look at the world around us through the eyes and ears of the sensors in your mobile devices, oh, there are stars. These stars are essentially sensor patterns, multimodal sensor signatures that are scattered around in the environment. And once we figure out those stars, which we are calling landmarks here, there are landmarks all at different places. Then we can use these environments rich with landmarks to do our localization. And that gives you, the paper at least says, gives you 1.7 meters accuracy, no infrastructure cost, right? You don't need to rely on anything, no Wi-Fi, no beacons, no triangulation, nothing, no GPS, nothing. You just need your phone with IMU. and there's no calibration needed. You can just use crowdsourced data, and from that data, you can do localization. Questions? Any questions, guys? Let me see what's on the chat. Okay, good. Okay, if not, then we'll finish up. We are done with unlock. And now we will move on to our next topic. And our next topic for today is probability review. Okay, actually our next topic is hidden Markov models for motion tracking. The theme of the next two lectures, of today's and next lecture, is that we want to, so unlock was one way of combining different kinds of information, but unlock was in some sense periodic, meaning I'm going to diverge. Oh, I found an opportunity to reset. Again, I'm going to diverge, reset, right? But there are other ways, other information sources in which at every point in time, you can combine IMU with some other information. Let's say you have GPS, or you have some motion model, meaning that if a car is going on the road, the car is not suddenly going to take a U-turn and go backwards. It doesn't happen, right? You have some understanding of how the car is supposed to move. If a human is walking, you know that the human cannot walk at 5 meters per second. That is just not possible, right? Or you know that the human is not going to undergo a Brownian motion, that is going to walk 1 step, go back 3 steps, walk 5 steps forward, go back 2 steps. It's not going to happen that way, right? So you have some understanding of what is supposed to happen in terms of the motion. And that piece of information, if you can mathematically quantify, then you can take that and the IMU and constantly mix them. So you don't let it diverge, and then reset. You constantly mix this motion model and the IMU information so that the divergence becomes curbed, becomes checked, and the system doesn't diverge too much continuously. Okay? This is what is called Bayesian filtering. And Bayesian filtering is essentially a topic in which you can combine any sources of information in a mathematical, systematic way. So we are going to talk about that in the context of motion tracking. But to do that, we need to do a quick recap of probability. I know we have computer engineers in the class, and some of these topics you have done in the past, but you might be rusty. But like our signal processing and linear algebra, we are going to do this quick. Great. Okay. Ready? Any questions thus far? Good. Like always, I think that math is easy, right? Math is fun. So again, I would say if probability was dry to you, it was not exciting, give me another chance. If it was exciting and if you understand all of this, you can snooze for a while. Okay. We have maybe 4 pages and then we'll start on hidden Markov models. Very good. Okay. So the way I think about probability is the following. Okay. You know, variables, deterministic variables, no probability, just simple variables, right? When we write a program and we say x equals 5, right? I think that is a variable. X is a variable. In fact, when I teach my son that, oh, when he's writing a code in some basic language like Scratch or some other things, I say, look, X is actually a container. The name of the container is X. And I take a value of 5. I take a digit 5 and I put it in x, right? I mean, that's how we think of a variable, right? It's a container in which you put a number that, and then when you say print x, it prints 5, right? So x is just a container. Random variables is no different. Random variable is also a container. X, random variable x. Just that instead of putting 5 in that container might have 1, might have 2, might have 3, might have 4, might have 5. So instead of putting 5 in that container, I'm saying that I could put 1, I could put 2. I don't know what this container has. It may be 1, maybe 2, maybe 3. So you know what? Why don't I look at this as a vector? Why don't I think of this random variable as a vector where the variable can have this variable x, this container x, can have any one of those values in that vector. See, it's not a real vector in the sense a vector typically is thought of as it has all the values, right? But I'm writing this as an abuse of notation where I'm saying, think of this as all the possible values that the random variable can take, put that in a vector. And I'll tell you why this way of thinking might have some benefits. Okay. So now you say, okay, x can take 1, 2, 3, 4, 5, but then which one does it take? Or with what probability? Is it all equal? X can take 1, 2, 3, 4, 5 with equal chance or different chance? Say, okay, there's someone else who's going to tell me that. Who's going to tell me that? Let's say there's a box. That box is called the probability box or the distribution box. And if you give a value as an input to that box will tell you what is the probability of that value that x can take. So if you ask that probability box or the distribution box, what is the chance that x will take 1? The distribution box will say the chance is 0.2, let's say, just as an example. So what is the chance that the x will take 2 as the value? That box says maybe 0.1. And so forth. So the box also, actually, let's fill up the values. 0.2, 0.3. Does it add up to 1? It does. Okay. So we say, what is the chance that the x will take value 5? The distribution box says 0.2. Right? So now you've pretty much defined what this random variable is. It's a container which does not take one value, it takes a bunch of values. And for each of these values, you have the chance, the probability with which that container takes that value. Okay. This vector is called the distribution of random variable x. Right? And of course, all this while we are talking about discrete random variables, not continuous. We don't have to worry about continuous random variables. We are in the discrete domain. Any questions thus far? I know you may not have looked at it this way, but if you're completely comfortable and happy with probability, you can stay where you are. But if you have struggled, I'm saying maybe try to look at things this way. Very good. Okay. So we have a random variable. We understand what is going on. So now let's say someone says, calculate the expected value of x. What is the expected value of x? What is the value that this bowl would have? What is the value that this container would have on average? Right? So then that means E of x is nothing but E of x equals 1, 2, 3, 4, 5. Right? Because we always think of x as all possible values that it can have. Right? And then we say, okay, x being 1, that probability is P of 1, this one. X being 2 is this. So x equals xi times probability that x equals xi. Right? when x equals 2, the probability that x equals 2. When x equals 3, the probability that x equals 3. That is what is the average value. So I can write this as 1, 2, 3, 4, 5 times P of 1, P of 2, so on, P of 5. Right? It's a dot product of those two vectors, right? Added up, right? I mean, dot product will add up all the values, right? So this is 1 times P1 plus 2 times P2 plus so on 5 times P5. That is the expected value of x. You know this pretty much, right? And remember, this is the distribution. Very good. Conditional probability. What is conditional probability? Well, you pretend, wait, what happened? You pretend that you know y has happened. What does this say about x's chances of occurrence? That's what conditional probability is, right? Px given y means someone tells you magically that y has happened. What does this tell you about x? Okay. You do not know whether y has happened. You just assume, you just pretend it has happened, right? Many people get confused with conditional probability. And I think it helps to always think, I do not know whether y has happened, but say God has told me it has happened, then what can I say? So for instance, probability rain given cloud. I do not know if cloud has happened, but I'm going to assume if it is cloudy, what is the probability it will rain? Right? I can reason about this kind of a thing. If I say probability it'll rain given Perseverance has landed on Mars. You can say, man, there's no connection between these two. Right? What is the chance of it's going to rain on Earth given Perseverance landed on Mars? Right? So in this kind of a setting, you can immediately say that this is the same as probability of rain. There's no value of having this, knowing this information that Perseverance has landed on Mars. Okay. So given something has happened, sometimes X, given Y has happened, sometimes X can get information from that. Sometimes it may not get information from that. That is what is the essence of conditional probability. Okay. So if we go back to our way of thinking of this as vectors, Px given Y can be thought of as Px equals 1, 2, 3, 4, 5, given Y, let's say Y takes values 26, 27 all the way till let's say 50. Y can take a bunch of values, X can take a bunch of values. And you could ask this question, what is the probability X equals 3 given Y equals 28? This is something people can ask you. Right? You want to know what is X equals 3 given that Y equals 28. Right? I don't know how to calculate that yet because I need to understand what is the relationship between X and Y. I need to quantify that. I need to get some information about that. Right? So before we solve this problem, let's quickly look at Bayes' rule, because Bayes' rule will give us the tool to solve that problem. Okay. So what does Bayes' rule say? Bayes says P of X given Y is nothing but P of X comma Y, means X and Y, divided by P of Y. Fine. You've taken me from x given y to x and y, and you've divided that by py. So what is pxy? Pxy means what is the probability that x and y both have happened. Okay. So then I'm going to write this as a vector. I'm going to say px equals 1, 2, 3, 4, 5. And y is 26, 27, so on till 50. And p of y is again 26, 27, so on till 50. Are you with me? P of xy is nothing but p of both x and y have happened. And I'm thinking of these as vectors. So x has to happen, y has to happen. But what does it mean this vector has to happen, that vector has to happen? It basically means I want to know the probability that every pair of these values have occurred. X equals 3, y equals 26. X equals 3, y equals 27. X equals 3, y equals 28. X equals 4, y equals 26. X equals 4, y equals 27. I want complete understanding of what are the probabilities of each of these two things happening. Okay. That means I need a matrix where the columns of the matrix are y. So y equals 26, 27, 28, blah, 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 till 50. And the rows of that matrix are x, which is 1, 2, 3, 4, 5. And a given element says what is the probability that x equals 2, this row, and y equals 28. Without that information, I cannot say what px given y is. I need this joint probability matrix. Right? And now you can think of, now you can see, right, if this is a bunch of values, a vector, a bunch of values, this is a bunch of values, the joint distribution is nothing but, it's telling me if I pick one from here and I pick one from here, I need that probability. Right? So you can think of pxy as two bowls, two containers, right? And I want to know for any value xi and any value yj, I want to give xi and yj to my probability or my distribution box, and it should give me a probability for that. Right? If I give xi and yj to my probability box or my distribution box, like we were doing earlier. Earlier, we were giving only one value, and it was giving me a probability for that. Now I'm going to give it two values, and it's going to give me a probability for that. That's the joint distribution. Right? So px given y is this matrix in the numerator. This matrix comes from here, divided by p of y. Now p of y means what is the probability y is 26? Let's say 0.01. What is the probability y is 27? Let's say 0.03. So on. What is the probability y is 50? Let's say 0.05. Of course, these should add up to 1. Right? Similarly, over here, all these probabilities should add up to 1, because if x is going to take any one of these values, and if I say the chance of x taking 1, chance of x taking 2, all of that should add up to 1. So similarly, py over here, all the probabilities should add up to 1. So this is basically px given y, but you can ask, what? I have a matrix on top and I have a vector at the bottom. How am I going to do any division? Of course, you cannot do a division, right? But when someone asks you this question, what is p x equals 3 given y equals 28, then you can answer the question. How do you answer the question? or let's say x equals 5, because I have that as the example below. So then you say px equals 5 given y equals 28 is nothing but px equals 5 and y equals 28 divided by p y equals 28. Right? And now look, this value is nothing but this square, because that is x equals 5 and y equals 28. So you take this value into your numerator. Py equals 28 is, let's say it's 1, 5 here. This is 26, 27, 28, 50. So you take this value in the denominator, and that gives you the answer to px equals 5 given y equals 28. Guys, question? I guess all these are familiar to you, so maybe I'm embarrassing you by talking about all of these. So I'll quickly finish up anyway. So this joint distribution, this matrix, can be thought of as an x-axis, a y-axis. X-axis, x takes the values of 1, 2, 3, 4, 5. Y takes the values of 26, 27, 28, 29, all the way till 50. And this is your probability of x comma y. Whenever you see this random variable x, y, think of it as x equals 1, 2, 3, 4, 5, or x equals all the values that x can take. Y equals all the values that y can take. And then reason about it, it will become clear. Otherwise, it's sometimes confusing if you've struggled with probability, right? I think it will help. Whenever you see this random variable in your mind, replace that as x equals 1, 2, 3, 4, 5. The way I'm trying to do it over here. If you try to reason about this, as you do the equations, it can get confusing. But if you reason like that, it can sometimes be easier. So this is nothing but p of x equals 1, 2, 3, 4, 5, y equals 26, 27, 28, 29, 30, till 50. And now for every value, let's say x equals 3 and y equals 28, there is some probability, which is this value. And this value is probability of x equals 3, y equals 28. And now there's a similar value for every point in this xy plane, right? So you can think of a surface over here. There's a surface, maybe I should draw that with blue. That surface tells you every probability for any given pair of values for x and y. That is the joint probability distribution. There's nothing different. If you understood probability distribution for that single variable x, if you understood this one, this is for a one-dimensional vector. The joint distribution is the same thing for a two-dimensional, for R2, two-dimensional space. This is a one-dimensional space, R1. This is two-dimensional space, R2. For every point in that two-dimensional space, you're asking what is the probability value for that point. That's joint distribution. Okay, very good. Next, let's talk about posterior and likelihood. So oftentimes we would want to, okay, oftentimes people think of posterior and likelihoods as one is probability of hypothesis given evidence, and the other is probability of evidence given hypothesis. Which one is which? Does anyone know? Posterior is what and likelihood is what? Okay. Are you guys familiar with posteriors and likelihoods?
I've actually never heard of posterior until now.
Okay. Anyone? Okay, let's start from scratch. Okay, so posterior is this, likelihood is this. Okay, we'll talk about it from first principles. So okay, so suppose I say, I was hoping that some of you would say, oh, I remember posterior and likelihood, and I set up the question for that. So suppose I say probability of murderer is John. This is a murder mystery that I'm solving. I say that probability that murderer is John, given the weapon of murder is a knife. And then I say another statement, which is probability that weapon is a knife given murderer equals John. My question is, which one is a posterior and which one is a likelihood? Posterior is typically the hypothesis, the probability of the hypothesis given the evidence, and likelihood is the probability of the evidence given the hypothesis. So in this case, what is the probability? Oh, sorry, which is the posterior and which is likelihood?
The former would be posterior, and the latter would be hypothesis, or sorry, likelihood.
So is that Adil?
Yes.
So you're saying this is posterior?
Yeah, because
Likelihood?
because the weapon would be the evidence.
Okay. Anyone else?
I'm just shooting in the dark here, but
Please.
maybe it depends on how you define hypothesis and evidence.
It depends on how you define hypothesis and evidence. Very nice. Very nice. I think that's the answer I was looking for. So shooting in the dark worked. In fact, I think in almost all cases, depends is the correct answer. So Lucas, any thoughts on when you can define something as hypothesis?
I'm not really sure.
Okay.
Maybe, I don't know, like something that how they depend on each other.
Okay. Any other thoughts?
Okay. Go ahead.
When you have some prior knowledge about it.
When you have some prior knowledge about what? About the hypothesis? About which one? The hypothesis or the evidence? Basically, the question is this the hypothesis and this is the evidence, or is this the evidence and this is the hypothesis? Okay. Here is the way I think you should think about it. Okay. When hypothesis is the one that covers the whole sample space. So suppose you are looking to find the murder weapon. Okay. And from the forensics of the murder, you know that the murder weapon could be a knife, could be a ratchet, could be a pistol, or could be a rope to strangle. Right? You have these 4 possibilities. And it has to be one. The forensic analyst says it has to be one of these 4. Right? So So this means you are trying to find the random variable W, meaning weapon, where W equals knife, ratchet, pistol, rope, right? All these four is the entire sample space. This covers all the possibilities. There's nothing else. Then that weapon becomes your hypothesis. Okay. Now, instead of weapon being your goal, suppose the murderer is your goal. Okay. And then suppose you know that the murderer should be someone inside this family that you figured out. And therefore the murderer should be one of John, Mary, Susan, Bob. John, Mary, Susan, Bob covers the whole hypothesis, whole sample space. There's no one else that's possible. Right? So evidence, so you should think about this as hypothesis covers the whole sample space this way. This is hypothesis 1. This is hypothesis 2. This is hypothesis 3. This is hypothesis 4. This is hypothesis 5. And evidence is some event that has happened that need not cover the whole sample space. Okay, let's clarify that as an example, but let's write this first. All the hypotheses should together span or cover the whole sample space. Evidence need not. Guys, does that make sense? Questions? Whenever you're looking at this random variable, if you know all the values that that random variable can take is all there is to be considered. That's the hypothesis. Let's look at an example. I tell you that there are 4 buckets, and the 4 buckets have different number of balls in them. The first one has 5, the second one has 4, the third one has 3, the fourth one has 4. And of these balls, the first bucket has 3 green balls, the second bucket has 1 green ball, the third has 2 green balls, and the fourth has 2 green balls. I tell you this. Now I ask you, what is the probability that the chosen ball is green given that the bucket it's chosen from is bucket number 3? Question to you, is this posterior or likelihood? Posterior is hypothesis given evidence. Likelihood is evidence given hypothesis. Okay. So is this posterior? Is this posterior or likelihood?
Is this evidence given hypothesis? Because hypothesis, well, the buckets here would be, well, there's only 4 possible buckets. So they would be like the sample space.
Fantastic. So therefore, what is this, posterior or likelihood?
I have like the memory of a bird, so.
Here.
Okay, so I guess since I said that the buckets were a hypothesis, it would be likelihood.
Excellent. This is a likelihood. You got it. Why? Look. For ball equals, if you want to write this as a vector, chosen ball equals green, can you write the full vector? You cannot, right? You only know green. Who knows what the other ball colors are? You don't know what the full space is. You don't even care. But if I say bucket, you can write 1, 2, 3, 4. That's all. That's your full sample space. Does that make sense? So here you're given an evidence and your hypothesis is this part, because your hypothesis, you know all the buckets. You know that there are 4 buckets and you're trying to choose from one. Right? Now tell me, what is the probability? What is the answer to this question? What is the answer? What is the probability that the chosen ball is green given that it's chosen from bucket number 3?
2/3.
2/3. Very good. Okay. Now let's do it the other way. What is the probability that bucket number 3 was used given that the chosen ball is green? I've picked a ball. I don't tell you which bucket it came from. But the ball happened to be green. So I tell you, pretend that the chosen ball is green. Or I tell you that the chosen ball is green. What is the probability that this ball came from bucket number 3? Is this a posterior or likelihood? Have fun. Sorry, I didn't hear you. Anyone? Is this a posterior or likelihood?
I think Hafan's muted even when he unmutes.
Yeah, Hafan, you're muted even when you're unmute. When you unmute, we still cannot hear you. Okay, show 1 finger for posterior, 2 fingers for likelihood. Very good. This is posterior. And this is clear why, right? Again, you can write 1, 2, 3, 4. You know the whole sample space. This one, you only know green. You don't know the whole sample space. You don't know all the colors that are possible. Right? So when you're trying to find which one of the whole sample space, that's the hypothesis. Very good. What is the probability? Now find the answer to this question. Probability of bucket equals 3 given chosen ball equals green. Who can give me the answer?
Is it 1/8?
Really? Ooh, okay. How did you get 1/8?
Maybe I jumped too quickly. I counted all of the balls and then there's 2 green. So I did like 2/16. Or I guess we should follow the Bayesian formula.
Yeah, tricky. Yeah. I mean, in a special case, it might be 1/8, but not in general. Okay. Okay, let's look at how to solve this. This is not as easy as likelihood. This is why, actually, last semester when I asked this question, what is the difference between posterior and likelihood? Someone kind of correctly said posterior is hard to calculate, likelihood is easy. Okay, which is true actually. The likelihood was easy to calculate. Posterior is harder. Let's look at why. Okay? P bucket given chosen ball is green is like saying, imagine this is X and this is Y. Okay? So Px given Y, it's not obvious. Lucas, you said that I added up all the balls and I added up the green balls, right? But then you do not know with what probability I'm going to choose different buckets.
Yeah, that's true. That's not, it's too big. Yeah, I think.
Right. It becomes big. Okay. So this is the right way to do it. So this is the posterior. X equals 1, 2, 3, 4. And we are asking, what is the probability x equals 3 given y equals green. Apply Bayes rule. This is nothing but pxy divided by y. Agree? This is Bayes rule. Now, pxy can be written as py given x times px. Why is that? Because if you apply Bayes rule on this, think of Bayes rule on py given x. That is nothing but py comma x divided by px. So py comma x is nothing but same as pxy. Pyx is the same as pxy. Right? Pyx means what is the probability of y and x occurring together, which is the same as what is the probability of x and y occurring together. So this pxy and this pyx are the same. And this pyx is nothing but py given x times px. So I can write this numerator as py given x times px. What is this? If this is the posterior, what is this?
The likelihood?
The likelihood. Okay. So I have now written the posterior as a function of the likelihood, but I have a bunch of other parameters, other variables, which is px. And px means what is the probability of choosing bucket number 3 divided by py, where py is what is the probability of picking a green ball. So we are not done yet. But we have written the posterior in terms of the likelihood. Okay. So let's define some terms here. This is likelihood. This is called the prior. Very good. Okay. We have not finished the problem, but we have brought it to some place where we have some handle. At least we cannot compute posterior directly, but likelihood we can do because py given x we've already computed over here. 2/3. And px, someone needs to tell you. So if someone says that the buckets are picked with equal probability, right? Then px is what? Suppose I say buckets are picked with equal probability. Then px equals what? So whenever you think of px, you think of p of x equals 1, 2, 3, 4. And that equals what vector? What is that probability vector? If I say buckets are picked with equal probability. Someone? Guys?
They're all just 1/4, right?
They're all 1/4. So if I say buckets are picked with equal probability, you can immediately replace this as px equals 3 is 1/4. So that also I know. This also I know is 2/3. I'm getting close. But I still do not know py. Right? Very good. Now what is py? Which is, what is the probability that the chosen ball is green? Okay. Now to do that, we need to introduce something else, which we call marginalization. Okay. So forget py for now. Let's look at marginalization in general. Marginalization says px is nothing but pxy summed over all y. Guys, suppose books, papers, they will always write these things and move on very quickly. If this seems confusing to you, fall back onto what we were talking about. Px, you can write it as P1, 2, 3, 4, 5. Y, whenever you see Y, you think of this as our previous example, 26, 27, all the way till 50. XY, you think of X as 1, 2, 3, 4, 5. And Y is 26, 27, 50. Once you look at it this way, it's no longer that hard. Now look. Px equals sum of Pxy. So Pxy, this Pxy is again that matrix, right? That joint distribution. Right? This is that matrix. What is the probability that X takes 2, Y takes 28, X takes 2, Y takes 43? For all those values, we need that matrix. And now you're saying add up for all values of Y. Okay. So that means if P, someone says Px equals 4, then that means X needs to be 4 over here. And now Y needs to be everything from 26 to 27. So I should add all the values. Probability X equals 4 is the same as probability X equals 4, Y equals 26 plus probability X equals 4, Y equals 27 plus probability X equals 4, Y equals 28, so on till probability X equals 4, Y equals 50. Right? The total probability of X equals 4 is scattered, is broken down into all possible values of Y. So we can write that as probability of X equals 4 is the same as probability of X equals 4, Y equals 26 plus probability of X equals 4, Y equals 27 plus all the way X equals 4, Y equals 50. This gives me probability of X. Does that make sense? Another way of thinking about this is, you remember that joint distribution, that surface. You take X equals 4. For all values of Y, you have different probabilities. You add up all these values, and that will give you X equals 4. Confusing? Clear? So probability of X equals 4, if you know the joint distribution of Y, you just add up for X equals 4 across all the values of Y. Good. So if that is clear, this is called marginalization. So if that is clear, now given Px equals sigma of Y Pxy, now what is that posterior? So remember the problem that we were looking at is, this is the posterior. Probability of bucket equals 3 given chosen ball equals green. And we had P of X given Y. This is the posterior. P of Y given X, this is the likelihood. This is the prior. Likelihood is 2/3, prior is 1/4, and we have PY, which we do not know. But now we want to marginalize PY. Okay. So what can we write PY as in this denominator? What can we write it here? Sigma P YX over all X. Huh? Does that make sense? This is the same thing that I wrote earlier, right? I wrote this earlier as PX as sigma over Y over PXY. Right? I'm just swapping the variables now. Very good. Now look, this PYX, what can I write PYX as? Apply Bayes rule. P Y given X times PX. Right? Hey, this is again the likelihood. And this is again the prior. But this time there is a sigma. There's a sigma over here. Very nice. So then we have a sigma over X, P Y given X, PX. Haha. So now we have this one and this one. Both are what? What are these two?
Likelihood.
Likelihoods. What are these two? What are they called?
Prior.
Prior. Now you know everything. You know this PY given X, you have to do it for every value of X, right? 1, 2, 3, 4. So if I tell you, for given this problem, what is, let's see you answer this. P Y equals green given X equals 1. What is that answer? What is that value?
3/5.
3/5. 3/5. 3/5 times 1/4, because PX is 1/4, plus, I'm doing the denominator basically, plus, what is PY equals green given X equals 2?
One-fourth.
1/4 plus, you keep doing the same thing. For X equals 3, X equals 4, you're done. That tells you the denominator. You know the numerator, 2/3 times 1/4. You have what is PY equal X given Y, the posterior. Any questions? Okay, if not, last point we'll talk about in probability is called the chain rule. By the way, guys, this is called the law of total probability. Let me just squeeze that in.
Professor, could you just repeat really quick how you got 2/3 for P y given X?
I sure will. Just give me 1 second. Yeah. Which one? Which one? Sorry.
I think I see now. I was asking about P y given X, but I think that's just 2 green over 3 total in box 3.
This one. This one.
Yep.
Oh, that one. Remember, X equals 3, right? This X is this X, which is this X.
Gotcha. So two green in box number 3. Right.
Exactly.
Okay. Thanks.
Perfect. Okay. Final thing is chain rule. This says probability of ABC. Now we are taking 3 random variables. Okay. Is nothing but, you can write this as the following. You can say this is PA given BC. Right? What is PA given BC? PA given BC is nothing but PABC divided by P of BC. You agree? This is what PA given BC is. So PABC must be PA given BC times P of BC. True? But now I can write that as P of A given BC times, now BC I again break it as B given C times PC. Does that make sense? Because P of B given C is nothing but P of BC divided by PC. So that means P of So therefore P of BC, which is this, is nothing but P of B given C times PC. Okay. So then I can write this in more generally, probability of, let's say I think of a bunch of random variables x 1 to n. This x1 to n, this means probability of x1, x2, x3, all the way till xn. I have n random variables and I'm looking at their joint distribution. I have a joint distribution. So I'm looking at the probability of all of these variables together. So I would, in our vector notation, I would say this is Px1 equals some vector, x2 equals some vector, x3 equals some vector, blah, 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 xn equals some vector. Which means their joint distribution would be an n-dimensional space. And then there's a probability P x1 to n. So every point in this n-dimensional space has n values. x1 equals I, x2 equals j, blah, 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 till xn equals k. And that point in that n-dimensional space will have some probability value. Right? This is what we are dealing with when we think of an n random variables together, their joint probabilities. Right? So we can write this Px1 to n given the above chain rule as P x1 given x2 to n. Make sense? Times, can someone tell me how to finish this? What should I write now?
Probability of x2 to n.
Sure, but chain rule is this. Basically, we want to write it in this form. We want to write it in this form.
P2 given
P2
x3 to n.
x2 given x3 to n.
Yeah.
Then
x3 given x4 to n and so on.
what is the last term? Okay, let's do the last one. P xn minus 1. Let me move this a little bit. Px minus n minus 1. Now what will happen? Given
xn.
Then is that the last term?
Minus pxn.
Very nice. Beautiful, right? It like nicely decomposes. You eliminate one by one. Right? And this will be useful when we talk about sequence of events ABC happening in time, or x1, x2, x3, xn happening in time. Right? And now you see the connection. Walking is like, where am I now? Where am I in the second time? Where am I in the third time? Where am I in the fourth time? And we are going to treat where am I in the time 1 as a random variable x1. Where am I in time 2 as a random variable x2? Where am I in time 3 as a random variable x3? And therefore, a trajectory will be x1 equals 1, x2 equals 2, x3 equals 5, x4 equals 7, and so forth, right? Different walking trajectories will essentially be different paths in this probability space. And that's how we will start reasoning about. So next class, we will start with Bayesian filtering, and we'll talk about how robots can walk and how we measure how this person is walking, and we'll combine them with motion models and so forth. But this probability review should give you all the probability background you need for what we're going to talk about. But I hope it also makes you see probability and not fear probability in any way whatsoever. Because, hey, if you've done linear algebra, if you've done vectors, it should be easy. Okay. That's all we'll talk about today. Questions?
Thank you.
Thanks, Adil. Questions? Okay, seems like not much questions.
Roman, can I talk to you about 499?
Sure. Why don't
After a few minutes, yeah.
Yeah.
I need to readjust for a presentation this week. So anytime you feel it's okay.
Oh, presentation to me?
No, not to me. I mean, it's a thing of do you see the email I sent you?
Have fun. Hold on. Let me stop the recording because the class is
right.
over right now, right? And we can talk about it after that. Okay, so bye guys. Oh, I think everyone's left.